All right, so by way of brief review, we're looking for the height at which the acceleration is 10% of normal. So I just did g divided by 10. And the term, like acceleration at that point, is this. Because remember that f sub g, which is big G m1 m2 over r squared, oh geez, is equal to mg, right? So that m cancels. And what is g but nothing but an acceleration? So the acceleration at some point in space, when we look at this statement right here, this gives us the acceleration of gravity on the surface, right? Because we're using r, and then r is the radius, so it's just telling us on the surface. So the acceleration at any point is going to be big G, mass of the Earth, over r plus h squared. And then that h, of course, being the height above the surface of the Earth, which I assume that's what we're asking for with the satellite. And this is all one number, yes? Right? So I guess, yeah, I don't know. Just do the math.
Can we just root it and then solve for h that way? Because technically, you're just finding the square of, like,
Yeah, you could. Yeah. Elsa's suggestion, I kind of like that suggestion.
It's easier.
Oops, just kidding. Elsa's suggestion is just take the square root of both sides, and then you get h is going to be equal to the square root of this gobbledygook mess right here, minus, just minus r.
It's just basically r. It's easier.
Yeah, that's good. Yeah. Because they asked for 10% in the problem. They said, where is the acceleration 10% of g?
And now we just gotta solve that.
Yeah, and so solve it and get whatever you want.
Okay, so what's
Okay, now
what's r?
what's r? R is 6.37 times 10 to the 6 meters.
R?
I think it's 637. Might be 27. That's also on your formula sheet thing.
Oh,
I
God.
think. Does anybody have that first page of the formula sheet? The constants page? Does that have the radius of the Earth? I think it does. Doesn't it?
R equals.
Yeah.
So
5.98 is the mass of the Earth. Yeah, the radius of the Earth. Oh, yeah. No dice. It's in your book, though.
Oh, yay.
I'm sorry. It's in your book on page. Well, actually, it's in your book on the back of the inside, on the back cover, on the inside back cover. It says astronomical data. Hey, look, it's the diameter of Uranus. Ha. Okay. Yeah, it is 6.37. So it's 6.37 times 10 to the 6 meters. Did I record that? That's most unfortunate. All right. Anyways. Now we want to know the velocity at that point. Since you already found the height, I mean, the easiest way to do this is just big G, mass of the Earth, over r plus h, yeah? And that'll give you a velocity of a satellite that stays in geosynchronous orbit at that distance. Yes? Okay. Questions? You should be plugging in the numbers. What did you get for h here? Do this now. Do it now. Now? Ah. Oh. Get out your calculator. Are you crazy? Mom, Dad, listen to my insane teacher. What? Okay. Anyways, do this. Do this now. What do you get?
It's a huge freaking number. I don't even want to say it.
Say it.
Okay. Hey, the scientific notation is
There you go.
like 1.36 times 10 to the. You're 6 or 7, I can't tell.
7? Okay, so it's 1.36 times 10 to the 7th meters. That's really far. Right? Because that's like 10 times, whatever, something 9 times the radius of the Earth, or 8 times the radius of the Earth. Yeah, it's very far. Okay, well anyways, once you've got that, you can plug it back in here and get the velocity, which would be astronomical, I think.
Well, that's just 5.35 is 0.16 meters a second.
What'd you get? 5 point?
No, it's 5,385.
5,385 meters per second?
Yeah, that's what I got.
Oh, that's not that bad, actually. So remember, this is not the radius, this is the height. And you subtracted the radius, though, right?
I just used the height.
Yeah, I mean, for height, you did subtract it.
Yeah, I did.
Okay. All right, good enough.
Idiot.
Any other questions on that?
So, since he didn't grade my notebook yet, do I just like leave it there?